paths and circuits. Here we have a whole bunch of vertices and we have a whole bunch of edges connecting them. A path is the route that we travel from one vertex to another vertex by following edges. The length, the number of times traveled from one vertex to another, from E to F is length 1. E to D is length 1, right? Even though they're not the same length, but these are length 1 because it's one edge. The distance between vertices A, B, written dA of B, is the shortest path between two vertices. DEF, that's D to E to F, that's path. And E to F to G to H to G again, back to D, that's another path. These are paths. The length of DGFE, that's D to G, that's 1. G to F is another one, so that's 2. F to E, that's 3. D to G to F to E is 3. Don't count the letters, but you can count the spaces in between the letters, the little dashes. Notice 3 dashes. Length is 3. The length of G, D, E, D, G, H is 5. Let's see about that. So G to D, that's 1. And then D to E is 2. And E to D again is 3. D to G is 4. And G to H is 5. A little trick of counting the dashes. 1, 2, 3, 4, 5. The distance from F to H. So F to H, it's just one step. I mean, we could go 2 steps to get there, but the shortest distance is 1 step. Distance between F to H is 1. The distance from H to E, however, so H to E is not 1. Notice the only way to get to it is I can go this way and then that way, or I could go to G, then F to E. Shortest distance is going to be H to D to E or H to F to E. In either case, it's 2. The shortest distance is 2. Circuit, a path that starts and ends on the same vertex. A to B to E to B to A, that's a circuit. Doesn't matter what you do in between as long as you begin and end at the same vertex, it's a circuit. D to C to E, D to C to E to B to E, and then back to A, and then back to D, that's a circuit because we started at D and we ended on D, so it's a circuit. Simple paths and circuits. A simple path is when you have no repeated edges. A lot of those paths we were doing before, we were going back and forth over the same edge. A simple path, no repeated edges. Makes it a little trickier. A, B, C, D is a simple path. From A to B to C to D. That's simple because we're not backtracking over the same edge. F to E to C to B to A to D and back to C is a simple path because we never went over the same edge twice. A to B to C to D to A. A to B to C to D and back to A is a simple circuit because we began at A and ended at A. It's a circuit and we never backtracked over the same edge. So it's a simple circuit. Euler paths and Euler circuits. Notice this is pronounced Euler, like an oil can, or the Edmonton Oilers. I always think the Edmonton Oilers are on the edge of their skates, and Euler paths are all about edges. Euler paths visit every edge in a connected graph once. An Euler circuit visits every edge in a connected graph once. 1. All vertices are even degree. We have 2 ways that you can have an Euler path. One is when all the vertices have an even degree, and we'll look at an example of that. So the path starts at any vertex and ends at the same vertex. So that's an Euler circuit. Or we have exactly 2 vertices of odd degrees, and the path starts at a vertex of odd degree and ends at another odd degree vertex. Euler is all about edges. Think the Edmonton Oilers are on the edge of their skates. The Euler paths, we visit each edge once. Let's have an example. We're going to look at an Euler path on this diagram. Visit every edge in a connected graph once. So let's say we're going to start with E. We start with E, and then we go to B. And then we go to C. And then to D. And then back to E. So we haven't gone over the same edge yet, even though we've come back to E. Then to A, and then to D. We've traced over every single edge. So that's an Euler path. Note, 2 vertices are odd, E and D. E has 3 edges that go to it. The degree of vertex E is 3. The degree of vertex D is 3 as well. Okay, and notice we started with E and ended on D. This graph has an Euler path. Here's an Euler circuit. So an Euler circuit is an Euler path that visits every edge once, but it starts and ends at the same vertex. If I started at E, I could go E to A to B to E to D to C and back to E. And we didn't go over the same edge, but we started and we ended at E. If we started A to B to E to D to C to E to A is an Euler circuit. We began at A, we ended at A, we never went over the same edge twice. Note, all vertices are of an even degree. Notice, okay, 2, this is degree 4, degree 2, degree 2. Remember, the degree is the number of edges that meet at that vertex. This graph has an Euler circuit. Hamiltonian paths and circuits. A Hamiltonian path is a simple path with no repeated edges, visits every vertex once. Euler was all about the edges. Hamiltonian is all about the vertices. Hamiltonian circuit is a simple path, no repeated edges, visits every vertex once, and because it's a circuit, it starts and finishes on the same vertex. And Hamiltonian, it's like he's standing the star. Think of the star as the vertex. Hamilton is all about the vertex. D to E to C to A to B is a Hamiltonian path. It visits each vertex exactly once. D to E, okay, there. And to C, to there, to A, back on that way, to B. We've hit every single vertex, and we didn't redraw over any of the lines. So that's a Hamiltonian path. D to E, to A, to C, to E, to B, and then back to A. Why isn't that a Hamiltonian path? Because, notice the E. We visited the E twice. We visited the A twice. We visited some vertexes more than once. For that reason, it's not a Hamiltonian path, but it's not Hamiltonian. A and E are visited more than once. So we have something called a Hamiltonian circuit. Let's say I went E to B to C to D to A. I've hit every single thing. When I went from E to B, then to C, so we're going into B, and we're coming out of, you can go in, you can come out. A circuit, we start with one vertex and we end on that vertex. The starting is we're coming out of that vertex, and the end we're going into that vertex. For Hamiltonian, we can't visit a vertex more than once. If it's the first and it's the last, then that's fine. For example, if we're looking at A to E, let's have a look at that. So, A to E, and then E to B, okay, and then B to C, and C to D, and D to A. Okay, so we've begun and we've ended on the A. We didn't go through the A twice. We've started at the A and we ended at the A. So it's not really the same as revisiting a point. It's a little bit different. So that's why it's allowable. That's why a Hamiltonian circuit is still Hamiltonian, even though we have the same vertex at the beginning and the end. You can't visit that vertex any other time or any other vertex any other time. You can only have one representation of each vertex. Let's say we were looking at an Euler path. B to E to A to D to B to C to D to E, and then back to C. Okay, so we've covered every edge, so it's Euler, but we ended up visiting a lot of vertices more than once. Like we visited B twice, we visited E twice, and C we visited twice as well. A lot of vertexes we visited more than once. That's why this would be an Euler path and not a Hamiltonian path. A path is traveling from one vertex to another vertex along an edge. A circuit, it's the same as a path, but you have the same starting and ending vertex. A simple path or a simple circuit is where you're not repeating an edge, so no repeating edges. Euler or Hamiltonian paths and circuits are simple, so you never repeat an edge. Euler path, visit every edge exactly once. An Euler circuit, visit every edge exactly once, but end where you began. A Hamiltonian path, visit every vertex once. A Hamiltonian circuit, visit every vertex once, end where you began. This is the Hamiltonian game. Hamilton came up with this game. He was really looking at the vertices that make up a dodecahedron, a 12-sided figure made up of a whole bunch of pentagons, made up of 12 pentagons. And he was looking at the vertices of a dodecahedron, and he was wondering if it was possible to make a continuous path. Let's say you start at A and then you end up at A, okay? Or you start at Q and you end up at Q, or you start up at S and end up at S. So the game, the Hamiltonian game, was to begin at one point and end at the same point, covering every single vertex. Remember, Hamiltonian, it's all about visiting the vertices. Give it a shot. Connect the vertices in a Hamiltonian circuit. And that's it for paths and circuits. Have a good day.